So in this lecture, we are going to evaluate the steady state error for proportional, integral, and derivative control, and how the steady state error could be changed by implementing different types of controllers. Now, let's see an example. We have a command signal Y reference connected to a controller GC of S. The gain is 1. U is the input. Here it is the plant. GP of S 1 by S plus 1 is a transfer function for the plant. This is the output Y. So it is fed back through unity feedback, and this is a negative feedback system. Okay, now this is the error. So what will be the time response of this particular transfer function? E raised to minus t u of t. Right. Now, say if error is 0, what will happen? If error equals 0, which implies u will be equal to 0, because e into 1 is u, right? E is 0. Now, if u is 0, what about y? Y will be 0, right? Now, yref minus y. Yref is a finite value, right? Yref is a finite value. So yref minus y, yref minus y will not be 0. Will not be 0. But our aim is to make the error 0. This is the condition. Okay. Our aim is to make the error 0. So this means that yref minus y is finite, means this system has a steady state error. Has a steady state error. Okay. Now yref minus y, let us go to the S domain. When we go to the S domain, what happens is okay. Yref minus y, this is the error, right, into GC is the controller transfer function, GP is the plant transfer function. This is equal to y, output y, right? What is GC into GP? 1 into 1 by S plus 1. So this is 1 by S plus 1. Okay, 1 by S plus 1. Now if we take L inverse, we get yref small y. This will become small y. Yref minus y equals y dot plus y. Because when you cross multiply, this 1 by S, 1 plus S will be multiplied to the RHS. So y plus ys. So if you take L inverse, y will become small y and ys will become small y dot. Okay. Now, what is yref from here? Yref is equal to 2 into y, right? 2 into y, which implies YSS steady state output equals yref divided by 2, right? Now what about ESS? Steady state error is yref minus YSS, right? Yref minus steady state output. YSS. This is the actual output now when t tends to infinity. This is equal to yref by 2. Yref by 2. Okay. Now if the transfer function, plant transfer function is changed, suppose we are using GP equals 1 by S minus 2. Earlier it was 1 by S plus 1. Now it has been changed to 1 by S minus 2. Then what is the closed loop transfer function? Closed loop transfer function is equal to GC GP divided by 1 plus GC GP. Right. It is equal to 1 by S minus 2 divided by 1 plus 1 by S minus 2, which is equal to 1 by S minus 1. This is equal to Y divided by Yref in S domain. That is why it is represented in capital letters. Okay, so this is the closed loop transfer function. Now this implies, what is Y? Y equals Yref into 1 by S minus 1, right? 1 by S minus 1. 1 by S minus 1 equal to from here. Okay, from here. Yref into 1 by S minus 1. Now, if we take Laplace transform in time domain, y of t equals Yref into e raised to t. So what happens when t tends to infinity? T tends to infinity, y of t will tend to infinity. So what happens to steady state error? Steady state error becomes Yref minus infinity. This is a finite value. Then ESS is becoming minus infinity for t tends to infinity. Of course, ESS is for t tends to infinity. Now, how can we stabilize this system? What can be done to stabilize this system? So which controller we used now? GC of S was just 1, right? That means it's a proportional controller. Okay. Now, let us give a try with the PID controller. Suppose you are using PID controller, then your GC will become Kp plus 1 by S into Ki integral plus derivative, right? Which is equal to Kd S squared plus Kp S plus Ki whole divided by S. What is the closed loop transfer function here? GCGP divided by 1 plus GCGP. So that will give you, I'm simplifying here and I'm going to write the final expression here. There is for simplification, we multiply numerator and denominator by S into S minus 2. Okay, that is, you can check it, but I'm writing here the final expression. It will become Kd S squared plus Kp S plus Ki whole divided by Kd plus 1 into S squared plus Kp minus 2 into S plus Ki. Please check this. Okay. Now, for this particular closed loop transfer function, we are trying to locate the poles by varying the values of proportional, integral and derivative controller. Values in the sense we want to get the desired poles by tuning the controller. So we know that if the poles are at -1, suppose this is a quadratic polynomial, right? So if the poles are at S equals -1, then the system is stable, right? Then the system is stable. That means the polynomial should look like s squared plus 2s plus 1. That should be the denominator, right? For this, what should be the value of kd? Kd equals 0, kp equals 4, then ki equals 1. Ki equals 1. So this is possible, right? By tuning, by appropriately tuning the proportional integral derivative controller, we can make the system stable. Now we have stabilized the system. The same system having the having the same plant transfer function, we used a different controller to stabilize the system. Okay. Now, if the system is unstable, we can manipulate this condition by using compensators and controllers. We know that, we have done it. If the system is stable, then we can manipulate and can get the desired performance by changing the gain k. Now, another example, g of s equals k divided by s squared into s plus 1 into s plus 2 for h equals 1. Again, the closed loop transfer function. The closed loop transfer function becomes k divided by s raised to 4 plus 3s cube plus 2s squared plus k. Right. This is the closed loop transfer function. Now, that means g by 1 plus gh where h is 1. Okay, that is what is this. Now we have a missing term here, right? S term is missing in the denominator. S term is missing in the denominator. That means the system is unstable. System is unstable. You can validate this. Validate using RH. You form the Routh array and apply Routh-Hurwitz criterion. Then you will find that the system is unstable. Okay. Now we try to add a PD controller to this particular system. At present, we have only considered the plant transfer function, which is g of s. Okay. Now we are trying to incorporate a PD controller. That means earlier we had this only, which was g. Okay, just g. Now we are trying to add a PD controller. PD controller in the sense it will be like kp plus kd into s. Okay. Now the output is y. Right. Again, this is a it's a negative feedback system. Okay. Now the closed loop transfer function will become, if we take this gpd into g, this is g plant. Okay, this is let it be g plant. Then gp divided by 1 plus gpd gp. This will be the new closed loop transfer function, which will be equal to kp plus kd into s whole into k whole divided by s raised to 4 plus 3s cube plus 2s squared plus kdks plus kpk. kpk. That is the missing term s now appears here, right? The missing term s. Without the controller, the transfer function was like that. The denominator of the transfer function was like that. It was the s term was missing. Now it has appeared. So we can adjust the values of kp and kd and can make it stable. There is an option of making it stable. So no zero coefficient now. S term is also there. No zero coefficient now. S term is also there. Okay. Now, so that's it. Our inference is for higher order systems here. This is a higher order system. For higher order systems, PD controller can be a solution for system stability, or rather, PD controller can be used to get the desired performance for the system. So that's all with this lecture. Thank you.